In today's video, we're going to discuss filling in the parameter estimates, using the parameter estimates to find the estimated means. Now, when you're just doing a regular analysis of variance or analysis of covariance, you can just check the box to ask for estimated means. But we're going to see where those means come from. Plus, we'll also discuss a little bit about how you can go beyond that to make some other predictions. We're going to use the chow data again, and first let's just remind ourselves of what that database actually looks like. We're going to have an x-axis will be our baseline axial length, and axial length at 5 years. And then we're going to look at lens type 2, which has spherical lenses that fit well or that performed well, and aspheric lenses. So there's 3 groups. Let's look at what we get. Let's double click on this graph and click on this light yellow and make it so we can see that a little bit better. So you can see that axial length at year 5 is definitely a function of where people started out. So if you started out low, your axial length at 5 years is going to be a lot less than if you started out at a baseline that was a little bit longer. So what we want to do is, in the analysis of covariance, we want to adjust for where people started so that we can compare the outcomes directly at 5 years, compare the lens types at 5 years. Okay, so having done that, let's get started. So first we'll quickly just go through and plug in our analysis of covariance. And before I get too much further, I need to remember to split my file by I so we maintain our independence. We come down here and we look at the options. We're going to look at lens type 2. We're going to compare our main effects. We are we want to do it 2-way, so we're going to put in gender as well. But we want to look at lens types within for each of the gender values for graphing, so we're going to put that second. Alright, now we go to options. We click on all 3 of these, send them over, compare our main effects. We can look at descriptive statistics. We want to look at the parameter estimates. Now, this is going to change us from is going to give us, in addition to our analysis of variance expected means, which are up here, to the parameter estimates that let us calculate that. And that's what we're going to do for that. Now I'm going to paste my my syntax so that I can add to this and do least squares significance tests on simple effects. So that's going to let me basically paired t-tests, or, well, not paired t-tests, but t-tests on the lens against each of the pairs of lens types. And here, I'm going to change lens type to gender, and that will let us add a spheric for the people getting aspheric lenses will be able to tell if there's a difference between male and female. So, it's somewhat questionable if this is legit post hoc test, but it's something that can give us an idea of the differences. All right, let's run that. Okay. So let's pause here. Let's get back to syntax. Okay. I'm doing lens type 2. So I need to put a 2 in there. All right. And here we get the number of subjects we have in each group for each eye. It's split between the left and right eye. We get the number of subjects. This is going to be useful for when we compute our confidence intervals, and we need to know the ends. Here we have descriptive statistics, and we're going to see how these change when we have our estimated means. For example, look at males spheric in the good control. That value is 26.29 compared to 25.45, a big difference. We go down to our estimated means. It's not 26, it's 25, and those two groups are virtually identical. So the expected mean, once we've adjusted for baseline, is a very different answer than just the raw mean. So you ask, well, which one is real? Well, they're both real. It's just that the mean after you've adjusted for baseline comes out to be this. Another thing that we need to look at is that in this particular estimated mean, it tells you what is the value of the covariate. The overall mean covariate is AL0 at 24.49. So it's a useful thing at this point to copy some information to Excel, just because we can use Excel for our calculator, and we'll do that. So I'm going to bring in an Excel spreadsheet, and then I'm going to copy some values. So let's, for the heck of it, let's put the estimates over here. This way we have our 24 value without having to look it up again. But and let's come up and grab the source table between subjects, useful for our finding out what our mean square error. Remember, we want this mean square error, which is a lot smaller than the mean square error if we just do the analysis of variance. But here is our parameter estimates, and we're just going to come over and copy these into here. And I think in order to clean up our stuff a little bit, we're going to get rid of the right eye. Just so we can keep everything straight. And here we go. All right, so now our question is, how do we compute? This is the model. If you think of a regression, it's y equals a plus bx. And so here, these are all listed under coefficients, or they're listed, you see these are all under b. I just said y equals a plus bx. Something that's a little confusing sometimes is the intercept is also a coefficient, and it's labeled under b, but this is equivalent to the a in y equals a plus bx. and it stands by itself. And then we have the baseline measure, 9.947. And the thing about this one is that it's a coefficient, so bx, well, what's x? In the case of looking for the overall estimated means, we take the mean value of AL0. So actually, if we go back to our graph, we're looking for the general mean when the baseline, if we take the baseline value. Now, these guys are actually a little smaller, so but it's still, overall, we get one value at a particular mean of the baseline values. So in the case of what we're looking at here, the mean baseline is 24.4. So if we look at 24 there's 25, 24.4 is about there. So what is the mean aspheric, good spheric, and bad spheric at 24.9? Okay, so here we go. And I'm just going to get rid of all of these values right here for now. And so we're going to multiply this B coefficient times 1 for the intercept. That'll just give us 3.48. For the AL0, we're going to multiply 24.4. That's why I can't remember that number. It's so hard. 24.4932. 4932. We're going to multiply that times this coefficient. Now, if we're looking at females, we're going to assign this a value of 1. If we're looking at males, we give it a value of 0 because the gender is it's F, female, if it's a woman, and 0 if it's a male. Lens type depends on which lens type we're looking at. So we're going to, if we're doing aspheric, we get 1, and then it would be 0, 0. So this first column, the way we're setting it up, it's a female aspheric person. So their value for gender is 1, the value for lens type 2 equals 1. A 1 is aspheric. This is a little confusing, but these values let's try and get that and see a little better. Okay. You know, if I was a great video person, I'd go back and edit this so you don't have to watch me futzing around here, but I'm sorry that I'm too lazy to do it that way. Okay, so we have lens type equals 1, 2, and 3, aspheric, spheric good, spheric bad. In this case, we're talking about an aspheric lens, so the other two are 0. For the lens types, only one of these values can be a 1. Everybody else has to be a 0. For gender, only this can be a 1. Everybody else here's a gender. It's 1 or 0 for male, 1 for aspheric, 0 for the other two. In the interaction term, the interaction term looks at if you're a female and you're aspheric, then, which is our case in this case, we're a 1. All the other values are 0. Now, I'd like to point out these little A's here are kind of annoying, although in this case it doesn't look like we have any A's where it's going to hurt us. So remember, our formula is y equals a plus bx. So the bx is the b times the x. And in the case of the intercept's x is always a 1. It's just we could just leave that out and just put in 348. The bx here is, the b is the slope coefficient, the b coefficient, times the x value. In this case, the x is the mean of everything. The gender coefficient bx, the gender b is that, times the x, which is a 1 because it's female. In this case, it's a 0. It never really counts for anything anyway. I'm going to get rid of those A's so I can just go straight down. So this is going to be 0 times 0. So really you don't have to multiply this because it's going to be 0 anyway. It's going to always 0 out if you're a male. But let's put it in there anyway. Equals 0 times 0. And how about that? That's actually 0. Let's just copy down here. And then, oh, I just, Johnny, copy from up here. Okay, so here we see we have, if you're lens type 1 aspheric, you take that coefficient times the value of 1 because you are this case. These are dummy variables. There's 3 dummy variables. There's, well, really only 2 that have a value. So you're aspheric, yes or no. If you're not, you're a 0. If you're lens type 2, you're a 1. Or if you're not, you're a 0. For lens type 3, you are not 0 or 0, so you're 0 down here. So you only really need coefficients for 2 of these. Same with gender, there's 2, so you need 1 coefficient value. All right, and this is our answer for the for if you're a female aspheric. And then we get our answer by taking the sum equals sum of all of these guys. And the answer is 24.85. Now if we come down here to our estimates of a female aspheric, we got 24.85. This was 24.843. I mean, it's close. There's rounding errors because the computer doesn't chop everything off at 3 decimal points. So that's pretty close. Just to kind of confirm this, let's look at this, the aspheric female who is spherical good. So again, the intercept is 1. It's the same mean for baseline. The gender is female. The male is 0. Now lens type 1 is 0 in this case. And lens type 2, which is spherical good, is a 1. Down here we have gender female aspheric is 0, and gender female, lens type 2 is spherical good, which is a 1. And now our number is 24.87. Female good, 24.868. So if you round that off, that's pretty close too. Well, what if you're a female and you're spherical poor? Poor fit. You come down here, you're still a gender 1, but now your lens type 2 is 0. You're not an aspheric, you're not a spheric, you're just 0. 0 goes in there, and nothing from lens type is contributing to your mean, your expected mean. You come down here, nothing is contributing, so we give that a 0. And when you sum, really the only thing that goes into this equation is the intercept, the baseline value, and if you're a female, you are shortened by 0.139, and so your final answer is 26.53. We come over here and we see we have 26.53. So that's pretty close too. Let's try again. This time let's do a male. Let's do a male spherical poor fit. So that's lens type 2 is a value of 3. So if we come down here, we still have the intercept. Because everybody has the intercept, we have a baseline measure of 24.49. Because everybody has the same, we're looking at the same mean baseline starting point. And then the gender, though, not a female, a male. So we could give that a 0. We can give that a 1, but notice it's still a 0 because now it's 1 times 0. And we are at lens type 3. But because we're spherical poor, but it's also 0 because it's 1 times 0. So in this case, and none of these fit because they're only female, all the males are 0s. So we look here and we have a mean of 26.67. So this is male spheric poor 26.67. Pretty close. And that's how you do that. Now, one of the things about this is if we look at our graph, what if a person it starts out pretty good, and let's say we want to know what is their predicted value in each of these groups if their axial length was really 23. Well, we can easily change that. Let's say we want the male spherical poor estimate when the baseline axial length is 23. Okay, well, it's 25.261. So 23 spherical poor, 25.26 is going to be somewhere in there. That's the predicted value when they start out with a short axial length. How close is this guy to being a predicted value, the estimated mean? So he's down here at 26.5 maybe. So let's put in 26.5 for his estimated axial length. And we get a value of 28.57. So if we go to 26.5, 28, okay, he's a little under what we would have predicted him up around here someplace. So he's a little under, but it's generally that's the advantage of having this equation. You can go beyond just the expected values, the mean expected values, and you can look at different points. It's kind of a sensitivity analysis. What's the difference between starting short and long in terms of axial length? Kind of understand the nature of your numbers a little bit better. And so basically that's how you use this regression equation that the parameter estimates give you. And it's all the same. You know, your expected means are certainly a lot easier to pick off just by looking at the estimates here and getting all your mean estimates. But if you wanted to do something else, and really you wouldn't do this, mess with this, if you just wanted to know the means, you just go pick it off here. When we talk about just linear regression equations, though, where there's no continuous or where there's no discrete categories, let's say we wanted to predict axial length at 5 years, only looking at spherical equivalence at baseline, axial length at baseline, you know, pupil size at baseline, we're going to get a regression equation with parameter estimates, but there aren't going to be any continuous variables. So we just we can plug in the mean value that we would find, or we could plug in various values at different levels of those. So what happens when you hold spherical equivalence and axial length constant and just look at small pupils and big pupils, and what's the difference there? So that's fodder for a different video. That's it.